In this video, I'm going to go over the unit storyline for Unit 8.1. Now, the entire unit has a driving question: why do things sometimes get damaged when they hit each other? That anchors the whole unit. And we're going to use in Lesson 1 experiences that students will share about cell phones being damaged, and using some statistics on how many cell phones get damaged each year. And we all know when you drop a cell phone, you look to see, did I crack the screen? So you're going to bring up those experiences. And what you're going to bring to the surface that sometimes the phones get damaged, but sometimes they don't. We're also going to relate this to other similar phenomena where sometimes there's damage and sometimes there's not, where we share experiences with other types of collisions, maybe with a bicycle and an object, or a car with an object, or even just a book and the table. So we think about all of these different collisions and we put together a chart, and you can see that this is a sample chart. Sometimes there's damage, sometimes there's no damage. We do figure out that at the moment of contact, the two objects are always touching, but we're not really sure about what happens a split second later. Is anything happening to these objects? And we start to kind of think about the variables that might be causing sometimes damage and sometimes not damage. Could it be that they're both moving, or just one is moving into the other? Could it be the mass? Could it be the speed? So we start to kind of think about these variables and then elicit questions about why do sometimes things get damaged when they hit each other. The lesson question is, what happens when two things hit each other? Remember, each lesson has a question that we are trying to figure out. The unit question is for overarching for the whole unit. So let's move into lesson 2. In lesson 2, you can see that we're using this cart track system. This cart's going to be used over and over again throughout the unit. And you can see that there's a CD case in front. There's a golf ball in front here. Looks like there's a little clay, molding clay or modeling clay with a washer usually used to weight the cart down. And so we're going to really explore collisions between different objects. It could be rice noodles or wooden stirrers or rubber stoppers, and we make observations. What we do realize is that sometimes there's a change in shape when the collision happens, and there's definitely energy that gets transferred, and there's also a force between the objects. And we're going to make a chart. It's kind of hard to see here, but we're going to have the energy perspective, and we're going to start modeling, showing these 3 little lines that follow the object, and that is representing motion. So we have one thing moving here, one thing not moving. This is the perspective right before the collision, the energy perspective. And then we're thinking about what happens during the collision. They actually touch each other and make contact, and then what kind of effect. And we're starting to think about kinetic energy. Then we're going to think about the lens of the force interactions or the force perspective. And so we realize that there is definitely a force or a push or a pull being placed on these objects by the other object. And so we kind of figure out a few things, but we are really not sure what happens to the shape of all objects. We can see maybe a metal hoop will bend when there's a collision, but we can't really see if the CD case bends. We can see that it cracks maybe, but we can't see that it bends. So we're wondering, do all objects change shape when they bend or pushed in a collision? So that moves us into lesson 3. We make a claim first about whether all solid objects bend or not when they're pushed during a collision. We actually look at some slow motion videos and also do an investigation with a mirror and a laser. And so when you have a collision with the mirror, the laser bounces. I will go deeper into it in our lesson 3 video. But what we figure out is that there's always a change of shape or some type of bend when the collision happens. And so we're wondering then, like, how much force does it take to deform a solid object? And that moves us into lesson 4. We're going to start looking at how much force you have to place on an object to get it to deform or break. And so what we're seeing here is you've got a push-pull spring. We're going to use them a lot in this unit. And we're pressing on this coffee stir stick that's across these two bricks. And as we press down, we're going to measure the force in newtons. We're also going to see how much that stick deforms by measuring with a ruler. And we realize that there's only a certain amount of force that can be pressed until it breaks. So we're developing the idea of an elastic limit. The bendability has a limit. And then we're also going to talk about that there's a breaking point, that at some point when the elastic limit is done, it's going to break. And so you can see the chart that we create that kind of summarizes all of this stuff is that when there's no push, there's no force. And notice we're starting to represent force with an arrow. The direction of the force is shown with the arrow, and the size of the force, the amount of force, is also represented either by the length of the arrow, or you can do it by the thickness of the arrow, but in this case, it's the length of the arrow. So the direction of the arrow shows the direction of the force, and the length of the arrow shows the amount of force. And so you can press a little bit, it bends a little bit. When you press a lot more and there's a lot more force, a strong push, more bend. A really strong force, there's going to be a breaking point and it's going to crack. And so we realize that the type of material, the shape of material, the thickness, all of these are variables that actually affect that elastic limit and the breaking point. Moving into lesson 5, we're going to be starting to consider other variables that affect the force. We know a stronger push is going to have more force than a lighter push. But how does the mass and the speed relate to that force? So we're going to be doing a new investigation using that same cart and track system, but this time it's set up with the plunger push-pull spring on top of the cart. And you're going to run that cart down the track into a brick. Now, this twist tie, that orange little twist tie, is set in the very beginning before you push the cart against the edge of the cart. So you know that starting position. And when that plunger hits the brick, it's going to move into the plunger. And when that happens, the twist tie moves out. And then when the plunger goes back to its original position, the twist tie shows how far that plunger moved in, and there's going to be a measurement of that right there. Now, what we're figuring out is Newton's third law here, that objects in contact with each other apply equally strong forces on one another. And so you can see we have this in the chart that when you've got two carts in a system, the force is going to be the same on both carts. And so there's going to be more than one investigation to figure this out. We also figure out that when we add more mass, let's say we put some weighted washers in here, or we push it faster, that we're going to end up with more force. So there's going to be increasing the speed or mass of a moving object, increases its kinetic energy, and it also creates a higher peak force, which is the highest amount of force it can create in a collision. So that peak force is represented by that twist tie measurement right there. And the faster it goes and the more mass it has, the higher that peak force is going to be. So moving into lesson 6, this is actually the end of the first lesson set, and we are going to take a transfer task assessment. This is a mid-unit transfer task. It's about soccer. So remember, a transfer task is when we take the science ideas that we've developed so far about kinetic energy, about peak forces, about damage. We're going to take all those science ideas and we're going to apply it into a new context, which is going to be soccer and soccer injuries. We also revisit our driving question board and realize we've answered some of our categories of questions about, what happens when things collide, but we still have more questions, and that's going to navigate us to the second lesson set. Moving into the second lesson set, we are going to be answering the overarching question, how are changes in energy related to the force interactions? So we are now really going deeper into the idea of kinetic energy. We started to touch on it in lesson 5 and 6, and now lesson 7, we're going to go deeper into kinetic energy. We're going to be using the CART track system again. You can see that we will talk about how much does doubling the speed or doubling the mass affect the kinetic energy. And we're going to find out, we're going to use an online simulation as well, and we're going to make some mathematical models to figure out the relationships between doubling the mass and doubling the speed to the kinetic energy. And we figure out that the kinetic energy of an object is directly proportional to its mass, and the kinetic energy of an object is proportional to the square of its speed. So we're going to use some mathematical models to figure that out. We also realize that the more kinetic energy an object has, the more damage it can do. And the more kinetic energy an object has, the more it takes to stop it, the more force or push against the direction of motion in order to stop it. And so we make a chart kind of summarizing what we figured out through those mathematical models, and we move into lesson 8. In lesson 8, we're going to be talking about where did the energy in our launcher system come from and where does it go? And so we're really going to be developing some ideas about potential energy, stored energy. We're going to use a spring to have some stored energy. We can also talk about a rubber band has stored energy. And they are stored when you change the shape or arrangement of those parts. And so you're going to press that cart up against the spring, and it's going to spring off and move towards a box. And we're going to measure how far that box moves. And then we're going to make a model. And we're really going to determine where kinetic energy is represented in this model. Where is it increasing? Where is it decreasing? Where is there no kinetic energy, like when something's not moving? Also, where is there stored potential energy when that spring is kind of crunched up right there and ready to spring out? We're also going to talk about contact forces. Where are those points of contact? So this will be a consensus model you make to kind of reinforce all of those ideas. In lesson 9, we're going to start to develop the idea of air resistance and friction. And you can see we have a CART track system again. There's a little index card, and that index card is going to kind of move back when the cart's moving this way. The air is going to push the card down a little bit. And so you can see we've got that plunger on the spring push-pull spring scale, and it's going to make the cart move and the card's going to move. So we developed the term of air resistance and also friction, which is that contact force between the track and the wheels. And both of these interactions are contact forces that push against the motion. So if the cart is going this way, those contact forces are pushing this way. Now, we started to develop the idea of using arrows and the size of arrows back in lesson 5 and named them free body diagrams. So we're going to use some of those techniques here, and you can see that we've got arrows pointing in the direction of the force. And we're also realizing that energy can be transferred from one object to another, including particles, like particles in the air. They get pushed, and particles can even push against the card or the cart. In lesson 10, we are actually finishing up the science ideas portion of this unit, and we're going to take what you can kind of consider an end of unit transfer task, because lesson set 3 is going to be an engineering challenge that uses all the science ideas. But this is the end of the science idea development, and we're going to take an end of unit transfer task, and it's going to be talking about why do some objects break or not break in a collision. We're also going to look back at our driving question board and realize we've made progress on a lot of questions, but there might still be questions about like cell phone cases. Why do they make phones not break? So those questions will probably appear in a category on your driving question board. So we're going to tackle those as an engineering challenge next. The transfer task in lesson 10 is all about baseball. So again, remember, we're taking those ideas developed, not talking about carts and tracks, not talking about cell phones breaking, but we're talking about baseball bats and baseballs and how we are understanding about mass and speed and peak forces and energy transfer apply into that scenario. In lesson 11, we go back and we realize we still have some questions about protecting these devices. And so we introduce the engineering design process. Students may have already used this before in earlier units. We are going to talk about some criteria and constraints and what all devices need to be protected. What would be the criteria and constraints? And we figure out that all protective devices have very similar criteria and constraints. They use good shapes. The materials that are used are going to minimize damage. Anyways, you'll develop those with your students, but no matter if it's a cell phone case for or a case to protect my cell phone or a case to protect my iPad, or there could be other types of devices. All protection devices have the same ideas of criteria and constraints that relate to shape, material, and structure. So we realized that we need to look a little bit more into the materials that we could use to create a protective barrier for our cell phones. And so we look at things like bubble wrap and cotton balls, and we go through all of these different materials here and realize that the amount of force that was reduced in newtons by that kind of cushiony material. So you can see like metal was not a very, let me make this a little bigger. Metal was not something that was very good at cushioning the system. And so like metal bumpers are something we can use as an example. There is some cushioning if they crumble. Actually, that's physics. That's in high school, crumple zones. But things that have air pockets are a lot better. So cotton balls, foam earplugs, styrofoam, those are the ones that get your higher numbers here. Bubble wrap. And so they reduce the amount of newtons more than things like metal and fabric. In lesson 13, we start to think about why those air pockets are so good at cushioning the protective devices. And so we develop a model. We use these construction paper rings to kind of figure out why these air pockets help reduce the peak force. And what we realize, and we watch a video and we talk about some of the unobservable mechanisms in these systems, that they very easily deform. And so they take some of that peak force and it helps it be a better material for protecting the devices. In lesson 14, we introduce the idea of stakeholders, and that stakeholder feedback is important when you're designing a solution to an engineering problem. So thinking about, what would the end user want in a cell phone case, or what do you want to consider as being important? And we may need to have some trade-offs. So if a consumer really wants a cool looking case, you might have a trade-off with some cushioning materials because people like that harder case look. Anyways, we introduce the idea of stakeholders and trade-offs, and every trade-off will have a consequence, but sometimes they happen. We also introduce the idea of a decision matrix and going through like how you make decisions using feedback from stakeholders or other people that you have surveyed. In lesson 15, we're going to now use what we've figured out to evaluate a different engineering solution. So this is another summative assessment, and it's talking about cheerleader protective headgear, because cheerleaders get a lot of head trauma when they fall doing their stunts. And so some people have thought about maybe headgear for cheerleaders to reduce the injuries. And so we take into account the solutions with the criteria and constraints and the trade-offs, and we see if students are able to apply those engineering ideas into this transfer task with cheerleader head protective gear. The very end in lesson 16, and this is optional, we talk about marketing different engineering ideas and how we can market them to stakeholders, and how you want to show how you took into account the stakeholders' wants and needs into your design. And so this is really not much about science, but more about business and entrepreneurship. So this is an optional end. And I will say that many people do replace this last engineering challenge with one that they've done in the past, because there's a lot out there that people have done, including Mars moon landers, the egg drops, all of those reduce that peak force and cushion the landing. So you can really use this and apply it to one of your favorite engineering challenges from years past. All right, hope this helps.